complexity of measures, right? Looking for a book to measure complexity.
Thank you, Valeria. Okay, so yes, so I work here at the university. I don't really know what your background is, so please stop me whenever if I go too fast, too slow. I have very little idea of what the general background of the audience is. So the talk is very, I work in mathematical logic, and inside mathematical logic, an area called computability theory, but which is not really computer science at all. And the talk is very foundational in the sense of foundations of mathematics. So don't expect the applications like you guys do in the institute. It's motivations are purely foundations, and the idea for the talk is to tell you about a little bit about this idea of computability and one of the conjectures that is still around. It's been around for a while, and what's the motivation for the conjecture. In the last two slides, I have some of my results, but probably we won't get there, or we'll be too tired by then. So we don't need to show that part, but we can see when we get there. How long is the talk, by the way?
We usually go for about an hour.
Okay. So yeah, but at least I'd like to get to state this conjecture called Martin's conjecture. I'll show you along the way by the end of the talk. Okay. So let me tell you a bit what do we mean, like at least people working in mathematical logic, when we say computability theory, which is not the same as computer science. So the objective for us is to study the complexity of mathematical objects that are countably infinite. So it's foundational in mathematics instead of in the sense that it studies the complexity of mathematics. Not the foundations, but the complexity of the different aspects of mathematics. I'm going to show you some examples. And computability theory, so that part of countably infinite, that kind of lays the setting for computability theory. So in computer science, there is all this area of complexity, like how the algorithms that are in P and P, P space, and it's usually about finite objects. It's not very clear the distinction here, but intuitively there you have, I don't know, finite graph and you want to find the path, or these are finite objects that you're dealing with. And here we are usually dealing with infinite objects. Now, there'll be some examples later in the talk. The first examples are simpler, and you'll see more what I mean. And then in mathematics there are objects that are not countable. They're uncountable, and there is other area of logic called set theory or descriptive set theory, where they study complexity of uncountable objects. So this lies kind of they are in the middle, and we see that's kind of like that's the level for the kind of the working mathematician. This level of countable infinite. For the mathematicians that work in the math department here, they usually at that setting. Finite objects, that's kind of like these small things, and this is kind of astronomy, like the very large objects. So we are at the level of actual mathematics. And now you'll see in a second.
I'm laughing because one of the main textbooks in category theory is called Category Theory for the Working Mathematician.
Ah, yeah.
The
right.
same idea that we want, the mythical.
Yeah. So the name comes because, okay, I'm going to show you in a second what the idea, how this notion of computable is, is the base for defining complexity. Okay, probably I'm assuming people know this concept. I want to call a function from the natural numbers to the natural number computable if there is some program that can calculate the function for you in whatever language is your favorite language. And a set is computable if the characteristic function for the set is computable. Yeah, you're good in this? And so in computability theory, this is kind of the paradigm. If something is computable, if some function, some set is computable, then it's easy. Those are the easy things. Those are the ones that are simple. If it's not computable, it's hard, and that's where the interesting things start to happen. In this area, if you're in computer science, no, everything is computable. Maybe it takes triple exponential time or something, but it's still computable, it's still a program. And you're trying to understand time bounds and time things, those are inside. So you would say in complexity theory in computer science, polynomial is easy, the rest is hard, and that's what I'm interested in. Here, computable is easy, and we study from there. So it's got, the hierarchy is pretty much the same one, this is just higher up in a hierarchy of complexity. But then there, so that's where we work. Okay, this is a thing which I guess you probably are used to. Also, yeah, so we're talking about functions from natural numbers to natural numbers, but that's just to fix a concrete definition. We could have used finite objects of whatever kind you want, and we just call whatever finite objects by zeros and ones and use natural numbers. So there's nothing particular about the natural numbers. It's just anything, something where you can code all finite objects you might ever want to deal with.
What's an object? What do you mean by a finite object?
Oh, like a mathematical object, I don't know, like a finite graph where each node has a color. You can encode that. It's an abstract finite object that you can encode with finite strings of zeros and ones. Or, yeah, or a string of characters. Or, yeah. Right, yeah, so I mean a mathematical object, but nothing in particular. Okay, so here are a few examples of non-computable sets, although these are the case, these are the set of finite objects, like I say that, but then these are the simplest ones to start with. So here are a few examples of sets that are not computable. I'm going to mention the examples along the talk, so I'll go slowly through them. It doesn't matter if you don't know the definitions of all of them, but let me just, since I'm going to keep on mentioning them, let's go through them one by one. So the first one, HT, is called Hilbert's 10th problem, which is the set of polynomials with integer coefficients in some number of variables, but some finite number of variables. They are finite polynomials, which have integer roots. So here, a polynomial with integer coefficients in a few variables, that's a finite object. You can call that a finite object.
Where all roots are integers.
But we are restricting to the ones that have integer roots, and that's what
all of their roots are integers.
all of no with some root,
one
at least one root that is an integer, at least one root. So a root will be a tuple because they have finitely many variables, a few variables. Right. So this set is not computable because deciding if such a polynomial has a root where all the entries are integer, that's not decidable by a computer. And that was Hilbert put that problem in his famous list in 1900, and it was solved in 1970. It's proved to be non-computable. So that's one. The whole gene problem, you've probably seen this one, is a set of programs viewed as strings of characters in your computer that do not run forever. Assuming you have, if you need more memory, you can ask for more memory, but you can keep on running. So some programs eventually stop, some kind of keep on jumping from one side of the program to another, and they never stop. So the halting problem is a set of programs that do not hold. You guys seen this one before? Yeah. Okay, this is more algebraic, so don't worry if you don't know what that is. So these are group presentations. In a group, you can represent in a group in algebra. You can represent a free group with finitely many generators, and then you can put some relations on them. So these generators relate according to this, and the relations are essentially just strings of generators. So they can be represented very simply, these groups. But picking the ones that are torsion free, meaning that for every element, if you multiply it by itself, you never go back to the identity. That's non-computable. Okay, this is a weird version of this one, but I'm going to use it later because it's a bit more complex. These are the polynomials, but now we see how a variable that is different than the others, x and many y's, they have integer roots for almost every value of x. Almost every here, I mean, for all but finitely many. For all the finitely many values of x, you can find y's that are root for your polynomials. It's a strange one, but it's It's part of the story that I want to make. Here's another true arithmetic. It's a set of sentences, like first order formal sentences about the natural numbers that are true. Here's a weird one called WS for well-founded. These are programs, so strings of characters, such that there is an infinite set of numbers, such that if you apply the program to one, you get the previous one. Again, it's a weird one, but okay, just because of to get the picture right on my examples. But you see it. Oh yeah.
When will notions of computability and decidability define?
Okay, so so Hilbert, when he asked for the question in 1900, he asked it in an informal way. Is there an algorithm? The people knew what an algorithm is. I mean, the Euclid's algorithm existed for 2,000 years. So he wanted an algorithm. He wanted a method to decide this. And he also asked for a method to decide first order logic in another of the questions. I think this second question. But only in the 30s is when they introduced the actual definition of computable. Gödel and Turing, and there's a few different definitions of computable. Kleene, the lambda calculus ones. So by the time he asked the question, there was no way to show there was a negative answer because you didn't know what it was. If people would recognize a positive answer, they would recognize an algorithm if they give it to them. But only after the 30s, people had the tools to prove algorithms didn't exist. Like this one is proving this. This is Houghton problem is from Turing. This is 36.
Can I ask a maybe a
Of course.
weird question? But
No.
if I give you streams of zeros and ones, and I ask you whether it's I ask you whether it's an integer or not. So I'm gonna give you an integer and then some string, or I'm just gonna ask you if they're all zero or not. Is that computable?
With an infinite string?
Yeah.
Well, the thing is that okay, so the inputs for these programs are finite objects.
Right. Okay.
So these are the programs.
I knew there was something else.
Yeah.
Okay.
So for instance, this Houghton problem, or any of these, you have the program, and you can start running the program, and the program can be telling you not stopping yet, not stopping yet, not stopping yet. Okay, 0, 0, 0, 0, 1.
Right.
Maybe if you see a 1, or if you see that it stops,
Solving problem. Yeah.
you know.
Yeah.
But if it all zeros, then
Cool. Thanks.
yeah. Okay, so examples good. Okay, so what is the idea for the talk? So the objective is, well, actually just for the story or for the I'm making for the talk, is to find some way of measuring complexity. I mean, this has been done in the 50s, kind of thing. Of measuring the complexity of these infinite sets. These are all infinite countable sets. That's why I call it like a ruler, which will measure, for instance, those examples and give you some way of measuring complexity, which one is more complex than which, and what can we do with that. So for that, at the beginning of the talk, which I guess it's already started, we're going to find an ordering. It's called less than or equal t. The t is for Turing. So it's called Turing reduction. It's an ordering on the subsets of the natural numbers, or equivalently on the functions of natural numbers, same. That allows you to compare the complexity of sets. Then we're going to look at a few of the most basic properties of this ordering on the sets of natural numbers, the same of complexity. And we're going to see that this is completely chaotic. I guess, well, I just want to mention some results. We want to see too much, but and then the third part is to try to find the structure underneath this chaos, and that's essentially this conjecture that I wanted to tell you about. It's called Martin's conjecture. And this picture, I don't know if you remember, when I was a kid, there used to exist these books that you see complete chaos, and then you look at them in the right way, and some shapes starts to show up. So that's kind of like Martin's conjecture. If you look at it blurry, then maybe you see some actual structure underneath. Okay, so that's what I want to talk about in the next 45 minutes. Okay, so let's start by defining this ordering relation to reducibility. Okay, so less than or equal t. So the idea is that a set B or a function B or something is Turing reducible to A if A contains enough information to calculate B. And I'm going to give you the formal definition in a second. And we're going to say that A is as complicated as B. So here is the definition trying to capture that idea. So, but this is for a function being computable in A instead of A. Okay, so it's similar. So we have a set of natural numbers. So we say that F is computable in A. So we defined computable before, now it's computable in A. If you can write a program that calculates the function F, but the program is allowed to use the characteristic function of A as a primitive notion. So your program is allowed to call is 17 a member of A, and something, it's usually called an oracle because it's not a real thing, answers that you yes, no, and during the program you can ask any question you want about membership in A. So characteristic function in A. Okay? So that's what it means to be computable in A. If A itself is not computable, then computable in A still doesn't need to be computable. And in that case, we write F is below A. Turin below A. Yeah, questions? Good. Okay, so here's an example, and let's look at this example so you guys see how it works. But probably I guess if you have computer science background, you probably can figure this out. So Hilbert's problem was a set of polynomials that have integer roots. Halting problem is a set of programs that hold. An example, Hilbert's program is Turing reducible to K. You see how to do that? Here is a proof of that. So you're given a polynomial. So we want to calculate. We write a program that is going to tell us if this polynomial has integer roots or not, and we are allowed to use this K as an oracle during our computation. So what do? We write a program. This is like inside our program we write a program. Q sub p. So p is the polynomial, and the program depends on p. And what does this program Q sub p do? It enumerates all the tuples of integers one at a time, and checks if they are roots of the polynomial. The polynomial is a finite thing with additions and multiplications. You can just easily check if it's going to give you 0 or not. If it gives you 0, you're like, good, it has a root. If not, you keep on going. You just enumerate them all, and you keep on going one by one through all the tuples, hoping that you will find some root. But you have to do is write the code. So you have to write the code for this program. So actually write the string that is the code for the program that does that. And then, okay, so if it finds what root, it stops. Otherwise, it doesn't. Otherwise, it keeps on searching. And then what you do to find if it has integer roots, you just ask the oracle if this program is ever going to hold or not. So you write the program, you get the string, and then you ask the halting program. So that's how you reduce Hilbert's program to the thing. Okay. Make sense? Cool. So these are the examples that I mentioned before, and that's what they look like according to this ordering. That's why I kind of cooked them up so that they were on it. So actually, Hilbert's tense and the halting problem are equivalent. You can reduce one to each other. You can reduce also K to the halting problem. That takes quite a bit of work, and that's the way they show that it's non-decidable in the 70s. Okay, so those are all the ones that I mentioned before. Yeah, they are in order like that. The strict reduction means you don't get reduction in the opposite direction. Yeah. So a ruler, this is something like a ruler. Okay, so if you're measuring the complexity, you're getting this is kind of, they are ordering according to complexity this way.
How roughly would you go about proving the strictness of these comparisons?
Let's see if okay.
That seems hard.
Yeah, actually, there is something that's going to show up later. Okay, so the halting problem you can show is strictly greater than 0. That's the usual proof that it's non-computable. And then we're going to see that kind of this one here looks like the halting problem relative to the halting problem. And so there is kind of a jump from here to there. So there is quite a bit of an analysis to understand what that looks like. But I think many of these can be reduced to, at the end, you're just showing that the halting, like, reduces things to the halting problem in some way to show that there is no way to compute them. So that's kind of a normal way, that's the easiest usually. Yeah.
You know, there's something a bit funny about the definition that you had before, right? Because you were saying we're comparing size of sets, and then you use a function. You say f is less than equal a.
Oh yeah, yeah,
yeah. A bit, you know, it
yes, right.
Breaks the category theories.
Oh, okay, yeah, because for us, like a set of natural numbers, or the function given by like the graph of the function, they can compute each other. So we see them as kind of the same thing. So yes, I'm abusing them. Yeah, I defined these, but I meant that. Since yes, so if you have the graph,
that's fine.
Yeah.
It's just kind of, you know, just explaining that.
Yeah, yeah.
But is it obvious that you can't hide like complexity in the encoding? Because what you're saying is ultimately you can encode all these.
Oh no, yeah, you can, right? Yeah, no, you can. So when I put the examples, I always mean kind of a nice, best natural encode, like easy natural encoding you will come up with. Like in all of them, in all of these examples, I'm sure all of you will come up with some way of encoding them that is kind of makes sense, and maybe you will come up with different ways, but they will all be equivalent. You could be trying to be tricky and find one where you encode weird things, and then in that case, yes. But right, in all of this, I'm referring kind of to the decoding that is. So right, so there is some work to kind of show that they actually all equivalent. I don't even know how to state it, but yes, in their life, yeah. At the end of the day, there is kind of, yeah. The simple codings, yeah. Okay, so what are the Turing degrees? So the Turing degrees, okay, so this is just this is the same definition I had before. I just put it up there because you're going to use it, of what it means to be Turing reducible. I used this notation in the previous slide. So two sets are Turing equivalent if they compute each other. You can use each one to compute the other. So that means they have the same information content, in a sense. You can compute each other. And the Turing degrees are the equivalence classes under these equivalence relations. So Turing equivalence is an equivalence relation. You can take all the sets of natural numbers and consider the equivalence classes. They are called Turing degrees. And now on this ordering or reduction is a partial ordering on all the sets. Right. So now we have an ordering of all that tries to capture all the possible levels of complexity that might exist among sets of natural numbers. A few basic observations so you get an idea of what this ordering looks like. A set and its complements are Turing equivalent. Yes. If one is in, one is in. If A is computable, is computable in everybody else. So that means this partial ordering has a bottom element. That is, the computable sets are there in the bottom. The rest are above. If you fix set B, the things that are computable in B, so in the ordering, everything that is below B must be countable, because there are only countably many programs you can write. So this is your oracle, only many countable programs you can write to compute different A's. So this partial ordering has this property that below every element is countable, and in particular, each equivalence class must be countable. No. So that means that the quotient, since each equivalence class is countable, but there are uncountably many subsets of the natural numbers, there are uncountably many Turing degrees. So the ordering is big. And until now, the examples that I was showing you are linearly ordered. They were like in that nice line. But that's not what the structure looks like. That's not what the partial ordering looks like. So Clean and Post, this is from the 50s. They build two sets that are incomparable to each other, so neither computes the other. and actually you can find anti-chains, so the collections of sets that neither computes the others that are uncountable. So it's kind of very fat, this partial ordering. So it doesn't look like that at all. And here's another theorem for that was from a bit later. I don't know if this is a bit more technical. Every countable partial ordering, so every partial ordering that is countable, you can embed it into the Turing degrees, preserving ordering and non-ordering. And so that two things are comparable in the partial ordering if and only if they are in the image. So inside you can have any shape you want. You can find like countably many Turing degrees have exactly the shape that you prescribed before among themselves. And you can embed it just between like 0 and the halting problem. That's already true. So you're already in that small piece below the halting problem. You get crazy behavior. And there are many more results showing that this ordering is extremely complex. Like the theory of this ordering it's not only undecidable, it's like very, very high complexity. There are many results showing that it's really complicated and messy. That's another, yeah.
Is there some sense of like how many different ways any fixed countable partial ordering can be embedded in this? Is it like, are they unique in some way? Or?
No, they're not unique at all. One way that is even like, you can even embed them, if they have the, you can even embed them as no, you don't need anything. Yeah, if they have to satisfy some distributivity, you can embed them as even as initial segments. Like you can pick one or this 1 degree, such that if you look at everybody below, it's going to be isomorphic to this guy. So they are really like, I'm saying.
Every countable partial order is the downset.
Yes, these are the Turing degrees, and you have your partial ordering P. I don't know, it looks like this. No, I wanted to do something. And then you can find a Turing degree such as this. Whatever is below it is isomorphic to this. So there is all sorts of crazy things that could happen there. I think maybe you need some distributivity. Right, okay, so you need a kind of a couple like very simple properties on this P. And you pretty much embed them all. So really you have like very strange behaviors. These like you can find all sorts of different structures inside there. Okay, so that kind of breaks a bit the nice ruler. And okay, so this is this some random picture of what it probably looks like. Okay, so these examples that I mentioned, it's not that I picked them up exactly to the NI line. All the examples that we know that come from anywhere mathematics, they will fit in this line. I mean, maybe there are a few more in between, I don't know, here, and a few more in between here. But all the natural examples that we know, they are in a line.
How do you know that Kleinian posts were not natural?
Okay, yeah, so I guess did I say that next? Mathematically, we don't have a definition of what it means to be natural. So Kleinian posts, when they build the examples, and that's how we build all the crazy ones. So we want to show that something is non-computable in something else. So I mean, it's an abstract, it's a mathematical proof, so it's not real. So we list all the programs, and we start building these two sets, making sure that none of these programs in the list compute one from the other. So it's kind of a diagonalization, going through all the programs and listing them.
So it's a diagonalization kind of.
Yeah, but it's
crazy.
It's gone crazy because because you don't want this one to compute that one, but at the same time you want to change it because you want to change them along the way. So you have to keep track of a lot of things to make sure none compute the other.
Can it be stated in? Can it be stated in? Can it be written down? With the axiom of choice, you never actually write down.
Oh no, you can write it down. Yeah. You can write it. I mean, it's not going to be they're not going to be computable sets, but they're going to be computable in K. So yeah, we can give a precise definition of these two sets. So there is precise definitions, and even like this with these torsion-free groups, they're finitely generated groups. You can get things that are weird, but still, like this requires like on purpose building things that are incomparable. It's kind of, they don't come up. All the ones that come up are in a line like that, and all the ones that don't, usually at some point you have to list all the programs and by kind of brute force make sure things don't copy each other. Yeah.
So do all like the classic problems of computer algebra, like word problems for finitely presented things, are all those of the same complexity as like check whether this presentation is torsion-free? They all belong.
Oh, okay. So I chose, yeah. So that's a good question. So I chose torsion-free so that I can have it up here.
Yeah.
So the word problem, which is to check whether the group is trivial, that actually is at equivalent to k.
Oh wow.
So, but then torsion-free is one level up. And then I guess you could say there is maybe some other question you can say there is another level up. And things with homotopy, with homotopy of whatever are at this level, also with trees. But the ones that you can say this group has this algebraic property, they're going to be in the line. Okay, so there is something kind of like all between kind of, okay, we try to define that ordering to give us this ordering of the natural examples, but we get that. So there is kind of something going on. And as logicians, we like to understand what's going on underneath. But right, so we have well, the first problem is that we don't know what natural means. But the one thing we know is that this is two properties, and I'm gonna try to explain a little bit what they are, these properties, but they might be a bit technical. The natural examples are constructible, and they are something called relativizable. Constructible in the sense that we don't use axiom of choice kind of to get them. And relativizable is, I'm going to tell you what relativizable means in a minute. And then using those, we are going to go from these examples that are relativizable and constructible. And we are going to consider certain functions from sets to sets. And on those, we are going to put an ordering. And that's going to be nice and tidy, like this one. So it's kind of, we are thinking the natural examples have certain properties, and then we're going to look at the things that have those properties. We can have an object related to them that we can see. Okay, this is the idea for what's coming up. So that's the part that when we look blurry, we're going to start seeing the structure underneath. Okay, this is loose. So let me tell you what relativization is. So there is one observation, it's an empirical observation, but it happens all over the computability, is that the set of functions that are computable in A, so remember A was the oracle and we look at everything computable in A, behave pretty much exactly like the set of functions that are computable. The reason is that almost everything we do, so the functions that are computable, you can define them, they have to be closed under some basic constructs. Well, I don't know, maybe just say while loops, for loops, if, whatever, something. And the ones computable in A, you can also use this primitive function compute in A. It's rare, like usually with the set of computable functions, what you use is that they are closed under these operations. But you rarely encode exactly that these are, you rarely go into the nuts and bolts of the Turing machine to see what's going on. So usually you use that you're closed under these operations, and both are closed under these operations of composing with computable functions. So almost all the results that, let me see. So relativizing a construction or a theorem or a proof to a set A means to change the notion of computable wherever this word shows up in your construction, your statement, or in your proof for the word computable in A. Usually you replace that like throughout your statement, your proofs, and everything works exactly the same. So there are many notions that are defined kind of in terms of the notions of computable, all over, in computability all over the place, but all those notions have a way of relativizing by assuming you have the oracle A. So here are examples. So K is a set of the programs that eventually hold, right? That's what we mentioned. halting problem. You can consider K relative to A. These are all the programs that use the function A as an oracle and eventually halt. So this is K. This is a new set. This is K relativized to A. Okay, I didn't use this one before. The set of programs that hold for finitely many x's, and you can relativize. And this is Turing equivalent to the torsion-free finitely generated groups. By the way, you can relativize this one by looking at the program with oracle A that holds for finitely many x's. Okay, this holds for almost every x. True arithmetic, first order sentences that are true, but now you put your set A inside your first order formulas. You can relativize the well-founded. You can relativize the programs. So all these sets have relativized versions. Okay, I just collapsed what I had right there, and collapsing again and again. So we could prove, well, I mentioned that it's possible to prove that you have this ordering among these examples. Well, the same ordering holds among the relativized versions. It's by the same proofs. And you can prove that they reduce to each other and they don't reduce back. All the same proofs go in the relativized case. So that means that each of the, for instance, for K, we have a function that given as oracle set A gives you the halting problem relative to A. And this is called the Turing jump. It's called the Turing jump because for every A, this new thing is kind of strictly higher up. So it makes you jump in here in the partial ordering for one thing. You always go up. You get something of strictly higher complexity. And the proof that this K is not computable in A is the same as the usual proof that halting problem is not computable. And it has the property that if two sets are Turing equivalent, then the respective halting problems are also Turing equivalent. So you get a well-defined function on equivalence on equivalence class. So I mentioned this. I guess I gave it out. What is the answer to what do you get if you apply this function applied to K itself? So the Turing jump of the Turing jump, and you get something that is equivalent to this set thing, which was the same as torsion-free. If you apply K to this one, so K to K to K 3 times, you get something Turing equivalent to this one, COF. That is a hold for all but finitely many x's. So this case kind of sort of ordering the things a little bit once we start applying these functions. I put the arrows, the dots here because the picture doesn't continue. You have to iterate infinitely many times before you get to this one. And like a lot more than infinitely many times. Well, I don't know, and whatever that means to get to that one. So the picture there is a bit, but they are still in a line.
Do we know if there's anything in between the ones without the dots?
Right. Okay. So there are many things in between, but nothing natural in between. Like in between these. There are natural things in between these two, and there are natural things.
Now means relativizable and
Constructive. Yes.
Okay.
But well, so the full thing is still a conjecture, but more or less yes. But yeah. Okay, so we are doing good on time. So I have two examples because these are the kind of the infinite mathematics. These are more algebraic. Well, I guess let me show you kind of two examples of functions that are of this sort. If you remember your algebra from I don't know when you. So I use a theorem in algebra that says that if you have a ring, you have a maximal ideal. An ideal is a subset of the ring that is closed under addition, multiplication by the ring, and maximal means there is no bigger set. Algebraists use these things. So how hard is it to find it? This is kind of what would be a question for a computability. If you're talking about countable rings, you want to find this maximal ideal. It's a construction they do in algebra a lot. So you have a countable object with a structure as a ring, and you want to find maximal ideal inside it. This is from my Spanish. So, okay. So let's formalize this question in the language that I was just developing. So, given okay, this is the power set of natural numbers. Given a subset of natural numbers, mi for maximal ideal of A, let it be the least Turing degree, such that every ring that is computable in A has a maximal ideal computable in mi of A. Okay, so essentially is, okay, so if you have A, so there are many rings that are computable in A. So what is the Turing degree that we need so that we can compute?
A ring is computable in A when what?
Okay, so, yeah, okay, so I'm skipping out of details, but yeah, so these are countable rings, so you can encode them, the elements by object, and you have to be able to compute the operations, the addition and the multiplication, and say who's the 0 and who's the 1. If you can do that, then you say the ring is computable in A. If you have some representation like that. And given the representation, you want to find the maximal ideal. Maximal ideals might not be computable in the ring, but somebody will be able to find them. So who's this somebody?
Does the positive Turing degrees have infima?
The Turing degrees, they don't have infima. No.
Then how do you know there is a least?
Yeah, no, we don't know this.
Oh, okay.
If there is one, we call it like that.
Okay.
I mean, we know there is a least because when I define it, we don't know.
Okay.
But then after the theorem, yes, we know. So you're right, so you're picking out that the definition could be incomplete if it doesn't exist, but in this case it exists. So the function is the halting problem. So if you have the halting problem relative to A, you can find these maximal ideals on the ring computable in A. And then there's a similar one. Okay, we don't need to explain what the Jacobson ideal is. It's another ideal they use in. You can do the same construction, and the two iterations of the halting problem is what you need to compute these Jacobson ideals, at least one. And they are the intersection of all the maximal ideals in the ring. Okay, so that was just a couple of examples. So all these examples that I mentioned and the relativizable functions have this property that they are Turing invariant. So they are well defined on the Turing degrees. So if two things are Turing equivalent, then the images are Turing equivalent. Okay? So they are we call them Turing invariant. So all of these examples mentioned so far are Turing invariant. And empirical observation, that's not an actual observation, but I tried to convince you, but it's only empirical. Whenever you have a natural Turing degree, it induces one of these Turing invariant functions in the way kind of we try to do like relativization.
The natural is still kind of with people with good intuition.
That's why they're empirical.
They're natural. That's fine. That's fine.
Oh no, right, and actually, but I'm being yeah. So I'm allowing things that people will say that's not very natural.
Ah, I see.
Within natural. So yeah. So.
But not vice versa.
But not vice versa, right? So nothing that So the things that are not natural, nobody would say they are natural. Like the things that I was saying, the set of programs such that there is an infinite sequence of numbers such that each one computes the next. You can say, is that natural? Well, natural in a sense, you can describe it in a few sentences or in a paragraph. That's anything like that I would consider natural. Yeah, and it's pretty much from the examples that we know, anything that doesn't at some point say, okay, list all the programs, let's work with them one at a time, try to avoid things. That becomes unnatural, I guess. But then the rest, everything you can define, all of them are included in there. Okay, so now we have this. Now we have the natural Turing degrees. They induce these Turing invariant functions, and we can compare functions. And we just say one function is below. This is the first definition you will come up with. one function is below another one if for every degree f of b is less than or equal to g of b. And so we know that among these, the ones that we talked about, for every oracle, they are in this order. So because all these proofs that we did, all relative, well, we didn't do that. I say they're doable, they relativize. So if you look at the corresponding functions, they are in the nice order. Okay, but this is not the end of the story. This is still the Turing. If you look at the set of all possible Turing invariant functions, you can easily cook up very weird things of all shapes and forms. So we still have, okay, but if we compare them on the limit, then we start seeing the structure that I want to tell you about. Let me tell you what I mean. Okay, that's the definition of Turing invariant functions. If we look at the Turing invariant functions ordered by this ordering that you just compare them everywhere, they are still chaotic. But if you look at them, define them, compare them on this ordering that I'm going to define now, kind of on the limit, then they become nice. So this is the ordering that you had to look at. So if a function is below another, these are functions from reals to from sets to sets. If there exists an a, such that for every b greater than a, f of b less than or equal to g of b. So this is like in the limit. Now, when you define something in the limit, there is a point after which something happens. Okay, there is an a after which f of b is below g of b. Except that here is not linear. So here you have the a here, and in the side, the cone here, for all the b's in here, you have f of b, g of b. And so that's going to be Martin's conjecture. Okay, so that's the definition that we just had, like I just mentioned again. So I'm going to use k, this notation, kf is kind of the composition of the two functions. You first apply f and then you apply k. I'm going to use it. And yeah, you get a new function that is strictly higher. So this conjecture, okay, I translated it from Spanish. This is coming from a talk I gave in Spanish. Conjetura de Martin says that every Turing invariant function, so it has two parts. The first one is that whenever you have a Turing invariant function, it's either constant or increasing. Increasing in the sense that x is less than or equal f of x. I mean, and it's not that the function is constant or increasing, it's equivalent in the limit. So this is kind of on this little cone up there is the cone, this cone up here. On a cone. It's going to be equivalent to something that is either constant or increasing. And among the increasing ones, you have this linearity property, and it's a bit more than linearity property. Whenever you have two functions, you have that either, this is a picture of there, either g is below f or g is above the halting problem relative to f. So this is saying two things. So okay, the picture is over there. Here you have f, and then this is kf, that is a function that is strictly above. This is saying that whenever you have any other g, it's either below or above. So in particular, the first is saying that f and g must be comparable, like one has to be below the other. And second is saying that it cannot be strictly in between these two. That if it's below, if it's not below, it has to be above, not only above f, but above the halting problem relative to f.
So it can't be a little bit above.
Cannot be a little bit above. It has to be a whole jump above. So this is a conjecture from the 70s. It's still a conjecture. And it has, we can talk about those letters later if you want.
We're not going you say that, I mean, ZF is the ZF that I know, and AG is the determinacy axiom?
Yeah, okay, so, yeah, okay, so I'll say something about that. So ZF is the Zermelo-Frankel's axiom for set theory, but the C from choice, usually you may have heard of CFC, which is a standard axiomatization for mathematics. The C is for the axiom of choice. This one doesn't have the axiom of choice. It has this thing called dependent choice, which is a weaker version. And AD is the axiom of determinacy, which is an axiom about some games having strategies. There is a version, if you want to work in CFC as usual, you cannot have determinacy, but you can have levels of determinacy. So if the functions you're working with are Borel, which is kind of, but most functions in mathematics are Borel, it's a class, a very large class of functions, then this still holds in CFC. If you want a larger class, you have to assume more of these determinacy axioms, but that's kind of a whole different talk about determinacy axioms. But morally, yeah, this is kind of what I'm saying is. So if you had choice, you could cook up functions where this doesn't happen using. But that was the constructible part that I was saying. Natural examples should be constructible. You shouldn't be able to build them using choice. So on determinacy kind of allows you to know like nothing can be built using choice. Kind of cleans up. It allows you to kind of have a nice statement like that. Okay, so this is a conjecture. Is known to be true for a subclass of the Turing invariant functions called uniformly Turing invariant functions. Actually, if part 1 is proved, part 2 is true for these uniformly invariant functions. And okay, I'm not going to go into details of what the uniformly there means, but all the examples that we saw before were uniformly invariant, so kind of the natural examples happen to be in this case. So the version of the conjecture that I'm presenting in the story of the talk, that's kind of known to be true. That's proved. But the full thing is not true. It's not known to be true yet. People are working on it for many years. And well, the connection to something I have worked on related to this, well, there is some. I have done work related to some aspects of the conjecture, which I don't know if I want to go too much into details, but which show that in a slightly different setting of many one reductions instead of Turing reductions, you can see where it comes from, and it has to do with some things in descriptive set theory called the wedge degrees. But I think I should stop kind of here and get questions from you. Any questions? Yeah.
So you said we know the post set has no meets or joins or anything else.
Okay. It has joins. That's easy to do a join. If you have two sets of natural numbers, you can build a new set where you put use the odds to code one and the evens to code the other,
Yep.
And that has exactly the information of both of them together.
So that's countable joins.
No, for countable, for
fine.
countable joins, you can put count element sets together this way, but what you get is not the least upper bound, not necessarily the least upper bound of all of them.
Okay.
So there could be something that still can compute all of them individually, but not in a uniform way.
Does any of this sort of conjecture try to look at, try to use these techniques of the delta nabla to make the post set prettier? Like this is I understand nabla to kind of be trying to make the post set prettier.
Right, but yeah.
Yeah, and is there hope that the post set would have more joins or more?
Well, in this case, actually, there is more to this. So these functions, like these ones, this is telling you they are linearly ordered,
Yeah.
so they are in a line, and it's telling you that for everything in there, you have a successor element, which is in the next one. So everyone has a successor element, and actually, the original there is another step that I missed that is well founded. So there is no infinite descending sequences. So what you get, it's an ordinal for the ones who know what that is. So once you have this ordering, you get an ordinal.
So is that what you mean when you showed that picture, and we could see the brown things in the middle kind of forming a...
Oh, no.
What do you mean by that?
This?
No, not this one, the colorful one that had all sorts of reds and yellows and stuff. And you said, if you look at that...
Oh, yeah, yeah. No.
What I was kind of going to ask is, what is,
Right, yeah.
Go
So
back.
I refer to this ordering that is underneath. It's kind of like there is
It's
the
like
partial
the
ordering is
spine.
this crazy thing, but then there is a spine. Somewhere there is a spine. Like the spine shows in the natural examples, but then you can prove that there is something going on. That spine actually exists in some way. It's not just like, yeah, it's not that our natural examples are restricted by our imagination or something. It's kind of, there is some mathematical reason why the natural examples are in a line.